Hello, welcome to Cornerstones of Math, and let us jump right into today's problem that is teased in my last video, which is linked in the description in case you haven't watched it. That is, we are now proving this inequality for the case of n variables. Given that fx plus fy over 2 is greater than or equal to f of x plus y over 2 for all real numbers x and y, let us prove that fx1 plus fx2 plus so on plus fxn divided by n is greater than or equal to f of x1 plus x2 plus so on plus xn divided by n for these n variables that can have any real number values. And of course n is natural number greater than or equal to 2. Of course the proof involves mathematical induction, but inspired by the proof given in my last video, we will use rather unusual kind of induction for this problem, which can be called forward-backward induction. In order to explain the procedure, let us call this generalized version of inequality proposition Pn. What we want to prove is that proposition Pn is true for all natural numbers greater than or equal to 2. And here, it is given that this proposition is true when n equals 2, which is the base case of our induction. And here's what we're gonna do. First, we will prove that if proposition p2 to the power of k is true, then p2 to the power of k plus 1 is also true. This will guarantee that the proposition is true for all powers of 2. Then we will prove that if pk is true, then pk minus 1 is also true. And combined with the first step, this will finally guarantee that the given proposition is true for all natural numbers that are greater than or equal to 2. So let's get right on to it. So the first step, here we have this induction hypothesis p2 to the power of k, which assumes that fx1 plus fx2 plus so on plus fx sub 2 to the power of k divided by 2 to the power of k is greater than or equal to f of x1 plus x2 plus so on plus x sub 2 to the power of k divided by 2 to the power of k. With this induction hypothesis, let us tackle this expression, which has 2 to the power of k plus 1 variables. Here we can group them 2 by 2. So we have fx1 plus fx2 as a group, then fx3 plus fx4 as a group, and so on. And in the end, we have fx sub 2 to the power of k plus 1 minus 1 plus fx sub 2 to the power of k plus 1 as a group. And for each group, we can apply the given inequality for 2 variables. So this is greater than or equal to, and let's write 1 over 2 to the power of k plus 1 here. Then we have 2 times f of x1 plus x2 over 2. Then 2 times f of x3 plus x4 over 2, and so on, until we have 2 times f of x sub 2 to the power of k plus 1 minus 1 plus x sub 2 to the power of k plus 1 over 2. So cancelling these 2's, then this plus 1 must be cancelled. So we have f of x1 plus x2 over 2 plus f of x3 plus x4 over 2 plus so on until the last term, which is this, divided by 2 to the power of k. Now let's consider the total number of terms. Up here, we originally had 2 to the power of k plus 1 terms. But since we have grouped the terms and combined them into a single term, by using the given inequality, the number of terms is now halved. So here, we only have 2 to the power of k terms. Therefore, we can apply our induction hypothesis p2 to the power of k, which was this, for these 2 to the power of k terms, which gives greater than or equal to f of, so x1 plus x2 over 2 plus x3 plus x4 over 2 plus so on until the last one, x sub 2 to the power of k plus 1 minus 1 plus x sub 2 to the power of k plus 1 over 2 over 2 to the power of k. And if we simplify terms inside parentheses, we have x1 plus x2 plus x3 plus x4 plus so on, until x sub 2 to the power of k plus 1 divided by now 2 to the power of k plus 1. Therefore, we have proved this inequality, which is the proposition p 2 to the power of k plus 1, and therefore we have proved the first part of our induction. If p 2 to the power of k is true, then p 2 to the power of k plus 1 is also true. So now the given inequality is true for all powers of 2. For the next step, let us prove that if the case for k variables is true, then the case for k minus 1 variables is also true. So now the induction hypothesis is as follows. Suppose that for some natural number k greater than 2, the following inequality holds for these k variables having arbitrary real number values. Now let's pull off the trick that we have used in the previous video. Since this inequality holds regardless of the values of these k variables, it must also hold for the special case when xk is given as x1 plus x2 plus so on plus xk minus 1 over k minus 1. Then the inequality becomes fx1 plus fx2 plus so on plus fxk minus 1. Then this last term becomes f of x1 plus x2 plus so on plus xk minus 1 divided by k minus 1. So this entire thing divided by k is greater than or equal to f of x1 plus x2 plus so on plus xk minus 1 plus, now this xk is x1 plus x2 plus so on plus xk minus 1 divided by k minus 1. So this divided by k. And let us simplify this part. If you simplify this, you will simply obtain x1 plus x2 plus so on plus xk minus 1 divided by k minus 1. Therefore, on the left hand side, we have fx1 plus fx2 plus so on plus fxk minus 1 divided by k, then plus 1 over k f of x1 plus x2 plus so on plus xk minus 1 divided by k minus 1. And on the right hand side, we have f of x1 plus x2 plus so on plus xk minus 1 divided by k minus 1. So moving this term to the right hand side, we have fx1 plus fx2 plus so on plus fxk minus 1 divided by k is greater than or equal to k minus 1 over k times f of x1 plus x2 plus so on plus xk minus 1 divided by k minus 1. So we finally have fx1 plus fx2 plus so on plus fxk minus 1 divided by k minus 1 is greater than or equal to f of x1 plus x2 plus so on plus xk minus 1 divided by k minus 1, which is the proposition p k minus 1. Therefore, we have the second conclusion that if the inequality holds for k variables, then it also holds for the case of k minus 1 variables. Therefore, by this base case and these two induction steps, we can finally say that this inequality is true for all real numbers x1, x2, so on xn, and for all natural numbers n greater than or equal to 2. And that was all for today's video. Thank you for watching and I will see you in another video.